Okay, welcome to day 9 of Cucci's College Now Pre-Calculus. You should be on file R.7, Radical Notation and Rational Exponents. So please go to that file now. Okay, so by the end of this lesson, you will be able to simplify radical expressions, rationalize denominators or numerators in rational expressions, convert between exponential notation and radical notation, simplify expressions with rational exponents. So that's the goal. This is all review. You have done all of this last year. Okay, so the nth root is a number c is said to be an nth root of a if c squared equals a. So that's just a general idea of how we find an nth root. Simplify the following. Okay, quick and easy here, guys. Square root of 36 is 6. Negative square root of 36 is negative 6. Cube root of negative 8 is a negative 2. And we know this because negative 2 times negative 2 times negative 2 is negative 8. The fifth root of 32 over 243. So we need to know what the fifth root of 32 is, which is 2. And the fifth root of 243, which is 3. The fourth root of negative 16 is, well, we have a problem, right? Can we multiply a negative number by itself an even amount of times and get a negative? No. We want to say 2 because we know the fourth root of 16 is 2, but negative 2 times negative 2 times negative 2 times negative 2 is a positive 16, so that doesn't work for us. So this is no solution. Okay? It's a non-real. I suppose we could say 2i. We talked a little bit about that last year, and we'll go there a little bit later on. Okay? All right, simplifying radical expressions. Consider the expression the square root of negative 3 squared. This is equivalent to the square root of 9 or 3. Similarly, negative 3 squared, when we square negative 3, it's negative 3 times negative 3, which is 9, right? Positive 9. Okay, so this is a longer page. Properties of radicals. You do need to know all of these properties. If we let a and b be real numbers or expressions for which the given root exists, for any natural numbers m and n, where n does not equal 1. If n is even, the nth root of a to the n equals the absolute value of a. If n is odd, the nth root of a to the n is a. The nth root of a times the nth root of b is the nth root of a times b, meaning if the indexes are the same, you multiply the radicands. Okay? The nth root of a divided by b is the same thing as the nth root of a divided by the nth root of b. And the nth root of a to the m is the same thing as the nth root of the square root of a raised to the m, or the nth root of a raised to the m. Okay? So if you don't know these, you should. Please put them down on a foldable or a note card so that you remember them, okay, and practice them. Okay, so we're going to simplify the square root of negative 5 squared. And we could start by dealing with what's on the inside. We know that the square root of negative 5 squared is the same thing as the square root of 25, right? And we know that the square root of 25 is 5. Now, we should also know that the square root of anything squared just becomes itself. So that's a quick, easy way. The cube root of negative 5 cubed, again, if you take the cube root of something cubed, it simply becomes this base here, which is negative 5. Okay, I hope you're all keeping up with me. The fourth root of 4 times the fourth root of 5. Remember, if the indexes are the same, you simply multiply the radicands, which gives us the fourth root of 20. And the fourth root of 20 is not going to be simplified. We're just going to leave it like that. Square root of 50. Okay, So here we start breaking things apart. How do we simplify this? How can we break down 50 so that one of those factors is a perfect square? 25 and 2, which is 5 square roots of 2. Okay, square root of 72 over the square root of 6. We know that this is the same thing as the square root of 72 over 6. 72 divided by 6 is 12. Okay. Can we simplify square root of 12? Well, sure. 4 and 3, right? Square root of 4 is 2. Square root of 3. Okay, so square roots are pretty simple. Let's move on to something a little bit different that you haven't done a lot of work with, and that's cube roots. So we have the cube root of 8 to the 5th, right? Okay, so we know that this is the same as the cube root of 8 to the 5th, okay? And we know that the cube root of 8 is 2. Cube root of 8 is 2. Raised to the 5th, which is 32. Okay, and this comes from your rules that we looked at the beginning. Okay, square root of 216, x to the 5th y cubed. So now we're getting into a little bit bigger problems where we need to start breaking exponents down, right, into perfect squares. So remember, the index here is 2. If it's not written, it's 2. We want that index to be able to divide into the powers, and right now they can't. So we do have to break this apart. Now, 216 is not a perfect square either, but 36 is, and 36 times 6 is 216. X to the 5th we have to break down. So we want the largest exponent that 2 divides into, that's smaller than 5, which is 4. So we're going to use x to the 4th and x. X to the 4th times x is x to the 5th, so it's broken down. And then y squared and y. Okay? So we broke this completely down so that we can simplify the majority of it. So I'm going to take my pieces that are perfect squares, and I'm going to take my pieces that are not and separate, so that it becomes 6x squared y, square root of 6xy. Okay? And like I said, we're going to do a lot of practice with these. Okay, square root of x squared, square root of 16. We know that a square root of a fraction is the same thing as the square root of the numerator divided by the square root of the denominator, which is just x over 4. Okay? So let's keep going. Perform the indicated operations. So we are multiplying, right? So we are foiling. 4 square root of 3 times the square root of 3 is 4 square root of 9, right? Multiply coefficient and then radicands minus negative 20 or plus a negative 20 square root of 6 plus square root of 6 minus 5 square roots of 4. From here, we're going to simplify. I know square root of 9 is 3, right? And I know square root of 4 is 2. And then these are what we call like radicals. They have the same index and same radicand, so we can combine their coefficients. Negative 20 plus 1 is negative 19. Okay? So we have 12 minus 19 square roots of 6 minus 10, or 2 minus 19 radical 6. All right, and again, I'm going through this quickly because you guys should already know how to do these. You've done these for the past few years. Okay, next page. Okay, next page. Let's try an application. The Pythagorean theorem relates the lengths of the sides of a right triangle. The sides opposite the triangle's right angle is called the hypotenuse. The other sides are called the legs. Some of the squares of the lengths of the legs of a right triangle are equal to the square of the hypotenuse. So that's your a squared plus b squared equals c squared. And I'm noticing now I've got a couple typos. Again, I apologize. Let me fix those right away. I don't know what a trig angle is, but we're going to call it a triangle. Okay, so everybody should know a squared plus b squared equals c squared. Again, nothing new. We're just going to use it. Okay. So Matt is building a dollhouse for his daughter. The dollhouse measures 26 inches across, and the slanted side of the roof measures 15 inches. Find the height of the roof. Okay, so what we're going to do is we're going to draw a picture. We've got this nice little dollhouse, right? And it goes like this. Okay, so we know that the dollhouse is 26 inches across, and we know that the slanted side of the roof is 15. We want to know the height of the roof. Okay, so how do we determine what this is? Well, we know that this entire length here is 26. We want this when we have this. Well, if the whole piece is 26, and we know that this is being cut in half, we could say that this is 13 inches. Okay, so we're going to use our Pythagorean theorem. 13 squared plus h squared equals 15 squared. Because I know the hypotenuse is opposite that right angle, that's going to be our c. Okay, so now we can run through this relatively quickly. I'm going to go ahead and get rid of that 13 squared, move it to the other side. H squared equals 15 squared minus 13 squared. And then to get h, I have to take the square root. So h equals the square root of 15 squared minus 13 squared, which is 225 minus 169, which is 56. Okay. And then h is about 7.5 inches. Okay. So the height of the roof is about 7.5 inches. All right. Rationalizing denominators or numerators. There are times when we need to remove radicals in a denominator or a numerator. This is called rationalizing. It's done by multiplying by 1 in such a way to obtain the perfect nth power. So essentially we're multiplying by something so that I can take the nth root. Okay? We want to make it pretty. Okay, so rationalize the denominator. We know that the square root of 3 halves is the same thing as the square root of 3 divided by the square root of 2, right? So again, we want to multiply by 1 in such a way that we can get rid of that radical 2. We want to make it a perfect square. So what can I multiply the square root of 2 by to make it a perfect square? Well, how about the square root of 2? And since we're multiplying by 1, it has to be the square root of 2 over the square root of 2. Multiplying fractions, we multiply numerator by numerator, denominator by denominator. We get the square root of 6 over the square root of 4, which is the square root of 6 over 2. And that's rationalized. There's no more radical. Moving on to the next one. Cube root of 7 divided by cube root of 9. So what we're looking for is something to multiply the denominator by so that that cube root of 9 becomes a perfect cube. Okay? So what are perfect cubes? Well, 9's not. How about 27, right? We want to stay within what we can get to. So what would I have to multiply 9 by to get 27? Well, we'd have to multiply by 3. So cube root of 3, cube root of 3, which is going to give us the cube root of 21 over the cube root of 27. And the cube root of 27, we know, is 3. Okay? All right, so let's go a little bit further. Pairs of expressions of the form a squared to b plus c squared to d and a squared to b minus c squared to d are what we call conjugates. The product of such a pair contains no radicals and can be used to rationalize a denominator or a numerator. So you're going to hear me yelling about conjugates constantly. So notice the difference here. The only difference is this sign in the middle, okay? Conjugate. So we're going to rationalize the numerator. So we're going to multiply by the conjugate. The conjugate is square root of x minus square root of y is the square root of x plus the square root of y. Remember, you're multiplying by 1, so it has to be the same in the numerator as the denominator. All right, so what we have to do in the numerator is FOIL. Okay, square root of x times square root of x is square root of x squared, which is x. Square root of x times square root of y is square root of xy. Negative square root of y times square root of x is negative square root of xy. And negative square root of y times square root of y is negative square root of y squared, which is y. In the denominator, we're just going to distribute. And then if you look in the numerator, what happens to that center, those two center values, square root of x minus square root of xy minus the square root of xy, those cancel out. And we're left with x minus y over 5 square roots of x plus 5 square roots of y. That's rationalizing the numerator. Okay. Now we're going to talk about rational exponents. Rational exponents are exponents that are written in the form of a fraction, essentially. What I want you to be able to do is go from that fractional exponential form to radical form and vice versa. You need to be able to go back and forth, okay? A to the 1 over n equals the nth root of a. So if I gave you a to the m over n, that's the nth root of a to the m. So essentially, n, if we're talking about this one here, n is the index, m is the power. Okay, so that'll be a nice way for you to remember where things go when we're switching them around. And just like we've said before, those negative exponents, we don't like them, so we tend to flip things, right? A to the negative m over n becomes 1 over a to the m over n. All right, so we're going to convert this to radical notation. Remember, denominator is index, numerator is power. Denominator is index, numerator is power. Okay, denominator, index, numerator, power. Okay, let's try another. We've got that negative exponent now, so we don't like those negative exponents. We're going to flip that, right? This is the same thing as this. If I want it as a radical, denominator, index, numerator, power. Okay. Okay, convert to radical notation. Simplify if possible, m to the 1/6. Denominator is the index, numerator is the power. So you should be getting pretty quick at this, right? All right, let's try another. Denominator, index, numerator, power. It's just another way to write it. All right, convert to exponential. So now we're going the other way around. Here's my index. Denominator is my index, and my numerator is the power. Now, notice that I put the 7xy in parentheses. That whole thing has to be in parentheses so that the 5/4 is included for the 7, the x, and the y. It has to be in parentheses. If you don't have the parentheses, it's incorrect. Okay, convert to exponential. Denominator is the index, numerator is the power. All right, when we multiply variables, what do we do with their bases? We add them. So this becomes x to the 5/6 plus 2/3. What do we need in order to add fractions? We need a common denominator. So x to the 5/6 plus 4/6. I got that by multiplying these both by 2, right? Which gives us x to the 9/6. And then to write that as a radical, the 6th root of x to the 9th power. Okay. which I could reduce if I wanted. 6th root of x to the 6th, 6th root of x to the 3rd, and we get x 6 roots of x to the 3rd. And we're going to do lots of practice with this in class. Okay, I know I'm at 20 minutes. We're just going to finish up these last slides and be done. I apologize for the overlap here. All right, simplify, and then, if appropriate, write in radical notation. We have common bases here. X plus 3 is our common base. So all we have to do is add these exponents. So we get x plus 3 raised to the 5/2 plus a negative 1/2, which is going to give us x plus 3 to the 4/2, or x plus 3 squared. Now, it wouldn't be appropriate for this to be put in radical notation. So we're going to leave this as x plus 3 quantity squared. It's no longer a rational exponent. All right, simplify, and then, if appropriate, write in radical notation. Okay, so what we have here is we have the square root of 7, the cube root of the square root of 7. So I can rewrite this. I know that the square root of 7 is the same thing as 7 to the 1/2. Now, you have to make sure that this is drilled into your brain. Okay, that's very important. Now, you also know that the cube root is the same thing as the 1/3 power, right? Index, power. So when I raise a power to a power and multiply, I could say 7 to the 1/6 power. And as a radical, that would be the 6th root of 7. Another way to look at this is the index here is 2, the index here is 3. You multiply. Okay? Last slide. All right, write an expression containing a single radical. All right, so square root of a, again, same thing as a to the 1/2. B, 6th root of b to the 5th is the same thing as b to the 5/6 power. Okay, so in order to do this, I need those bases. I know the bases are different, but I need the exponents to have the same denominator. Okay? So what I'm going to do is I'm going to look at 1/2, and I'm going to write it equivalent with a denominator of 6. Okay? So now they both have the same denominator, the same index when we go to radical, right? The index is going to be 6. And we use our numerators as our powers. Okay. That's the end of the lesson, so please make sure you come in with your notes completed and any questions that you might have, and I will see you tomorrow. Bye.